Mm.
Um, go onto your studio again. Just not this. On YouTube, in the top left. No. Oh, indeed. Click on that one. Go onto your studio again.
I think we're live then.
Not this. On YouTube, in the top left.
Am I live then? Okay, my meeting's starting.
Indeed.
Hello?
Oh,
Hello?
yeah, can you hear me?
Yeah, I can hear you.
Nice.
Okay, so I'm gonna email you some practice problems, and I kind of just want to go through that.
Okay.
Okay, I sent it. And for these practice problems, I want to start in chapter 3. So let's start on slide number 6, the first question asking about the thermal sensor.
Slide 6. Where is 6? Oh, thermal sensor.
Yeah.
Measurement system behavior, chapter 3. Okay, this one, right? A thermal system. Oh, okay, a thermal sensor. Okay.
Yeah.
Okay. So you have the right? The gem book.
Yep, I'll send it.
So the gem board will be closed from day after tomorrow, right?
Yeah. What do you normally use again? You said it was like a Microsoft something something?
Yeah, I use usually the Teams, but I believe there would be some things like Jamboard for sure. But I am not aware of that anything. I'm pretty sure there would be something, right?
Yeah, probably.
I have to find some. Okay, right. Okay, so the time constant is provided here, and you have to find the okay.
If it's temperature, I'm gonna guess it's first order, like a thermometer or something. So I'm assuming first order.
Yeah, it's a first order system. Usually, mostly the thermal sensors are first order.
So this symbol is my what's it called? Error fraction?
Oh, this tau.
No, this is
Tau. Usually tau is known as time factor or time constant, or you can call it sometimes time period. So
Oh,
basically, it's a period. Yeah.
this is the dynamic error. My bad. That's the symbol for dynamic error. Okay, so for the first part, I got 2.3 seconds for
Yeah.
the time, so no. Now it's asking what constant would be required to meet the requirement.
Yeah.
So then I guess I have to use this again and then solve for tau this time.
Yeah, basically here you can consider the time as a, you said that for safety it has to be less than one. So for require you can put the time constant as one, and then again you can find, sorry, you can put the T90 as one, and then you can calculate the time constant from there.
So you said put the t as 1?
Yeah. So like what I mean is that the one you consider T90, let's say when 90% of the response times, if I say it, so that is equals to, you got is 2.3 into tau, right?
Yeah.
Yeah. So now they says that the time constant has to be 90% response time should be less than one, right?
Yeah.
So yeah. So it means T90. So basically has to be less than equals to 1. So that's the maximum. So you can consider this criteria. So you just plug it down, the 2.3 into tau is less than equals to 1. So tau would be equals to 1 over 2.3.
Oh, equals to. Okay, so that question is good, and um, let's do slide number 5, the first question with the electronic scale.
Slide number 5. Electronic scale has sensitivity. Okay. Okay.
So for this one, I'm a bit confused as to like what I should be using.
So basically, it's most of it theoretical. So static sensitivity is equals to the output over input, right? So if you call it static, as you write output over input, I can see. So it means that value is 2, right? The static sensitivity. So 2 is basically the output voltage, let's say voltage, divided by kg in input, right? So when the range is from 1 to 210, so basically it means the voltage output required would be 2 volt to 20 volt, right?
Hmm.
Yeah, so that's what they are asking, that what should be the range of voltage that the voltmeter must be used to measure.
Okay. So 2 volts. Okay, so for my solution for the second part, what is the significance of increasing the static sensitivity? I wrote that increasing static sensitivity changes and increases the output range as well as the input range proportionally. Is that what they're looking for?
No, actually, I mean, the like good way to put it, like a different way. It's like if you can say four, maybe 3 4 point, like resolution. It's in improved, and the voltage range is higher, the basically the voltage range, which is the output, it will get larger, and the accuracy will be also increased, the third point. And the other point you can say about possible saturation, something like that. Like if static sensitivity is quite high, like towards higher side, the voltmeter may saturate or exceed its measurement capacity. So that's one. But three important point, you can say that resolution will increase, voltage range will increase, and accuracy would be greater. So these points you can mention.
Okay.
Yeah, voltage range increased, the resolution will increase, which basically will increase the precision of the measurement and also accuracy of the measurement.
Okay. Okay, we can do the question underneath that with the percentages.
Hmm.
correct for the first one of 75%?
You mean the 75% response time, right?
Yeah.
So how much you it shows? It's 115.
Yep. Seconds. 0.115.
Oh, 0.115. Maybe less it should be. Okay, let's see. So you got tau. Where is the tau? Okay, tau is 0.4, right?
Yeah.
Yeah, okay, that's okay. That's correct. Now, 75% response time. It means where you did this should be. Okay, so you did empty. Okay, 0.75. No, I think it should be this one should be 0.75 should be equals to 1 minus e to the power t over 0.4, right?
Um, M of T is T. Mm, mm, it's in the one. Mm.
So here you consider 0.25. I think that should be 0.75.
Right. Then equals to dynamic error. Right. Okay. So then right over here, isn't it supposed to be my dynamic error, which is just what's not completed? So that's 25%. Like if it's a 90% for the rise time and it completes 95% of the step function, then the dynamic error is 10%. So it's like it's whatever's not done.
Mm, I think usually the first order, if you recall the first order system, the response, for the single input, isn't it that the time is equals to the initial step input into 1 minus e to the power that value?
Um, it's 1 minus like the ratio equals to e to the power negative t over tau.
Yeah, that's fine. That part is okay. But isn't it that response time, what you find out after solving the first order system, isn't it it's something like, let's say t is equals to the initial input over 1 minus e to the power t over tau? Isn't it the formula? Like, or, I mean, the solution when you get after solving the first order equation?
After solving the first order. What's U naught?
Not, let's say it's just step input, the magnitude of the step input. You can consider that, or initial kind of a.
Okay, hold on. Let me just grab my formula sheet.
Or sometimes it's called the total time also, like a total time t0 or t total.
So the
So
formula
basically,
I was
yeah.
looking at, if you go to page 6, is that one. Is my
Uh,
dynamic error 25 or is it 75?
let me see. Uh, ah, okay. Tau t y infinite. Okay. YT. Yeah, so if you use this equation, I don't know how it's written. This equation, isn't it? Uh, yeah, if you use that one, y infinite minus y0 into e to the power minus t over tau is equals to y infinite minus yt. So basically, yt is equals to y infinite minus y infinite into e to the power minus t over tau plus y0 into e to the power minus t over tau. Something like that, right?
I was using this part, the 1 minus mt, because I know this is 0.25.
Okay, what is defined as here tau? The tau is defined as the error or
The tau is the
dynamic
time constant, and the t I'm assuming is response time.
error. T is e, no. T should not be the response time. Okay, it's little bit. Okay, we have to see how it is defined as.
Okay.
Because because it's a on definition, but usually when you solve it like anyway when you solve it, the time basically here it should be like if I call it the time in terms of time, that at t it should be equals to the total time into 1 minus e to the power t over tau. So when you do the t minus over the t total, let's say, that should be equals to 1 minus e to the power minus t over tau. So let's say when you consider 70% or something, or 20% time, or 90%, basically this whole equation would becomes, let's say, 75 or 95, whatever you want to do.
Wait, where did this equation come from? The one that you wrote?
That's basically, it's basically response, what do you call, response equation, or the first order responsing solution. So when you solve the first order equation, you will get this one, because this dynamic error, whatever the equation you got here from the formula, it's coming from here, this equation. So that's the first equation you will get when you solve the differential equation in the which represent the first order system or second order system. So that's the differential equation. After solving, the first step would be this, to find this solution. Once you find the solution, after that you can calculate the error. So the error comes afterwards when you find the solution.
Okay.
So this is the first steps. For example, you see the in the question they provide you the one kind of system. Now this system you can't solve it here because it's you don't know the ut and something, but we know that it's a first order system and we know the tau. So you got the tau from the equation and you know the first order system. Now this is what I just wrote, that is the general solution of first order system. It's a general solution of a first order.
For a step input?
Yeah.
Okay. On page 7, this is my entire formula sheet for first order. The kind of
Hmm.
equation I'm seeing is the tau y prime plus y equals to ku au. Or are you talking about the output?
Mhm. So here, if you see uh, y0, so if you ignore the y0, right, like if you don't consider the like initial condition, you can see that that's the formula we got. I wrote, right?
equals to Ka times by negative Ka e to the power negative t over tau. Your formula was are we considering y naught as 0?
Usually initial condition, we should not, yeah, here you see the question itself says that your initial condition is zero initial condition.
Where's this with it? Just a second. Oh, assume 0 initial conditions.
Yeah.
So then if we, in this formula over here on the 7th page, I'm circling.
That's the more general formula.
So if we get rid of that because it's 0, then it becomes this at the bottom.
Yeah.
But your thing has a 1 minus.
Yeah, from this equation, if you take Ka common, isn't it? It's become e to the power t over tau.
Wouldn't it just be equal to Ka times by negative e to the...
No. So, so you see here, okay, see the equation they wrote Ka plus into the bracket K something y0 minus Ka into whole into e to the power minus t over tau, right? So here plus, yeah. So you ignore them, then it becomes, yeah. So y0. So if you can like if you put y0 as 0, what would happen? It would becomes Ka minus Ka into e to the power t over tau, right?
Right, and then yeah, okay.
Yeah. Then it will become Z.
So how does Ka equal to time though?
Now, usually, where is your question there? Ka, Yt. So here, the Yt is why it's the displacement, right?
Yeah,
It's not the time. Now, what is the K here?
0.4. Or sorry,
No.
4, just 4.
Where is the... Oh, no. I'm not saying the tau.
The tau is 0.4, but the K is 4 because it's right in front of the U of t. Because if you look at the system equation, it's like tau y prime plus y equals to K AU of t.
Okay.
Or equals to K of A in that case.
But that equation, then you will get the y, right?
Yeah.
The y and the total. So Ka is kind of total. If you see, if you think about it as a kind of system, then Ka would represent the peak magnitude or peak amplitude, right?
Yeah.
Yeah. So if that is so, then you can convert it into the time domain, or into the time, basically, like how much time it takes and how much that is. Now, if you see mt, so this you see the mt. What is this magnetic ratio?
What page are you on?
And in page 8, or no, 7, I think.
Okay.
7. So what is this magnetic ratio? It says
Like what is the magnitude ratio?
yeah.
I assumed it was just the dynamic error minus 1.
No, it's not in terms of dynamics error. I think usually, yeah.
It's output amplitude at steady over input amplitude.
Yeah, so the is the amplitude ratio, right? And that amplitude also will be corresponding to the time ratio, right?
Yeah.
So that's why you can substitute like that. So if the amplitude is, like let's say uh, amplitude, if I write it like that, amplitude at any time and amplitude at maximum, isn't it, you can write it in like kind of it's equals to or proportional to the time it will take over total time.
Right.
So you can usually convert it that way. But the equation I wrote, usually I knew it before. I mean, yeah, for first order system, that's the one we used to calculate the the times and those kind of stuff, related stuff. Uh, but there you should have also got something like the total time.
I'll send you my formula sheet.
Yeah.
Okay, sent it.
Formula sheet. Why this is dynamic Fourier yt mt tau t. Yeah, tau t. Okay, okay. I think you can use this magnitude ratio. I think there is nothing different than that. It's mentioned. 10% of dynamic error. Yeah. So basically, you can use this one. What we are doing. Yeah. So the magnetic ratio, that actually it gives you much more close value in terms of the time. So here it means so mt, when it says that 75% rise time or 90% rise time, you can put it like mt is around, let's say 75. That should be close to the 1 minus e to the power t over tau.
For this question, it asked for time formula sheet. So is response time the same as rise time?
Response time as a rise time.
Yeah, response time has a rise time.
So this a you put kind of you can say that. So usually the response time. Okay, so rise time, usually it's also referred to a response. Okay, so usually rise time is defined as the measure, like how quick the yeah, detector response when there is a change in the signal. So so response time is basically when you put some in some input into the system, or a detector, or a signal detector, anything, how the time it's requires to give some output, that is usually call it the response time. And usually the rise time, it's kind of related to this, but it's defined something different way. So it's defined as the how much time it takes from the electric signal, it's reach from low value to high value. So that's usually the rise times referred to.
Okay. So in this case, the reason that m of t equals to 75
Hmm.
is, could you reiterate why it's equal to 75 again for the m of t?
So it's the magnitude, right? Magnitude ratio. Magnitude means that the ratio between the amplitude at that particular time over the highest magnitude, right? So the highest magnitude or the highest amplitude will be corresponding to the total time, right? The total time, which is in this case 0 0.2 or whatever value. Now at each time, the amplitude that should be, that the ratio at that okay, sorry, maybe I should write it. So what I mean is that if you check maybe page number 8, yeah, yeah. So magnetic ratio mt, right? So that is basically, it's nothing but amplitude at any time over the peak amplitude, right?
Is that the same definition as amplitude out at steady over input amplitude? So does that mean input amplitude is the max?
Input amplitude is the max. It's not actually input, but you can say it's that the maximum peak amplitude.
And then output amplitude at steady is the same as like amplitude at time t?
Yes, output amplitude would be the one, yeah, we are considering there. Yeah, yt. What you mentioned, the yt, that's actually our output amplitude.
Yt is output. Okay. Sorry, keep going. So it equals to that ratio, okay?
Yeah. So now this ratio, you can see that basically you can think about it as a in terms of displacement and time, right? So you can think this amplitude is kind of analogous to the displacement, right? For if you consider a simple dynamic system, how the one particle moves and corresponding to the time, right?
Okay.
So so here the velocity will be also come into the picture, but usually that's how it will be defined as like that. Uh, do you get the what I mean?
Mm, and then amplitude, like at time t over amplitude total, that ratio is equal to time at t and time total.
Total time, yes. if maybe this if I draw it, maybe it will be helpful for you. You recall the carb, how the carb would looks like. So if I draw it like yt, let's say this is the carb yt over the t over tau, t over tau, the carb actually it's represent something like this. You see something like this, first order system. But the error which you want to calculate, you are trying to work with the error. You remember that you are doing that little bit tau. So the error will looks reverse, this tau over t over tau. It would looks reverse like hyperbolic. So when it says the response time uh, up to some corresponding value, so it should be 1 minus that value always. So let's say if 75% would be somewhere here, 75% response time this, then the corresponding error should be 1 minus response time, right?
Hmm.
So that also you can use always.
Yep, the corresponding like dynamic error is 1 minus response time. So that would be
Yeah, yeah.
0.25. And then what do I
uh,
sub in the 0.25? Not for M of t.
you mean the one you are doing the before, right?
Hmm.
Yeah, so there you put the wrong, I think. When you do the in the so when you are solving it in page number 5, you used instead of error you used, you know it should be 0.25. So 0.25 should be equals to e to the power minus t over 0.4, but you used the opposite one.
Okay, so on page 9, the
Hmm.
error is 0.25, which equals to 1 minus m of t. What I wanted to do was rearrange for m of t and then just sub it to be equal to, yeah.
Oh, why a 1 minus m of t error?
Oh, that's true. I could just straight up do this. E to the
Ah, okay.
power.
Yeah, yeah, yeah. It's right. One minus that. Yeah, yeah, yeah. Yeah, correct. Yeah, you are right. Yeah, because one m of t is one minus that. Then one minus it would be that. Yeah, yeah. You are right. Yes.
Okay, and then 0.25 equals e to the power negative t over 0.4. So 0.693 seconds in that case.
0.693. Yes, it can be. I mean, it should be around that. Yeah. So zero
Hmm.
point 0.5, 0.2. ln. What is ln 0.25?
Ln 0.25 is negative 1.386. So,
Into 0.4, so it should be around 0.554 maybe.
yeah. And then divide that, multiply by 0.4.
Yeah.
0.25. Oh, yeah, somehow. Okay, this is way easier then. I could have just done this. I don't know why I was equating to 1 minus m of t and then equating it to 1 minus e to the power negative t over tau. I could just straight up do it this way.
Yeah, 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 but I think in page number 5 you use the same formula, but you put the wrong values. I mean, you did 1.25 is equals to 1 minus e to the power t over tau.
I did 0.25 equals to 1 minus m of t.
Yeah, yeah.
That should be right. That's dynamic error 0.25 equals to 1 minus m of t. Then I rearranged and solved for m of t.
No, no, what you did is that 0.25 is equals to 1 minus e to the power t over tau. You did this one.
Alright, on page 9.
Yeah. If you check the page 5,
0.25 equals to,
so you remember here you got 0.75 is equals to e to the power minus t over 0.4.
Hmm. Oh, I forgot the one minus over here where you circled.
Yeah,
Because it's supposed to be m of t equals to 1 minus e to the power negative t over tau.
yeah,
0.75 is m of t, but there's just no 1 minus to make it 0.25.
yeah,
Okay. Well, at least I know how to use the general equation more now.
yeah. That's
And just wondering, why is time at t, or like amplitude at x, equal to output amplitude at steady? Like, why can I make the assumption that I could sub one in for the other?
sorry. Which one? Can you point out?
Um, why is amplitude at whatever x value equal to output amplitude at steady? Because my formula sheet says it should be at steady, and then you said that it could be at any x. How do those two have a correlation?
Which equation exactly you are referring to?
On my formula sheet for the
Uh,
first order system magnitude ratio, on the very right, there's a formula for output
yes.
amplitude over input. Yeah.
Yeah.
So it
So
says, yeah, keep
uh,
going.
yeah, it says m omega is equals to 1 over root over 1 plus omega square tau square. That one?
No, it's the one there, it's the magnitude ratio. It's like 1 over root 1 plus omega. Yeah, and then to the right of it is the output amplitude at steady over input amplitude.
Hmm. So what is your question?
Why is output amplitude at steady equal to output amplitude at any value of x? Because you were saying in the formula from before, it's like a at t equals to a total.
A at t is equals to a total.
Yeah, so
No.
why is a of t equal to output amplitude when it's steady, like at a steady rate? So assuming t equals to infinity or something.
Mm, what I said is that like I as far as I remember, mt is or the magnitude ratio is represent the amplitude or output amplitude at any given time over the uh, peak amplitude.
Yeah, so I get why peak amplitude is equal to input because that's all you're gonna get. Like what you put in
Uh-huh.
is most you're
Uh,
gonna get out.
uh.
So then how come amplitude at steady for the output is equal to output amplitude at any point?
Okay. So output amplitude with steady. So you, how come it becomes like that? I think they. So it's becomes okay. So it's for not step input. It's for sinusoidal input, right?
Yeah.
So the sinusoidal input, I think, I'm not sure, but you can maybe represent the output the or the magnitude ratio as the ratio of our steady state output amplitude over input amplitude.
So that's only for a sinusoidal input of like a
Yeah,
sine omega t. But
yeah, yeah,
generally, we use what you said, or
yeah,
any
yeah, yeah.
x over total.
Yeah, yeah, the general term is always like output amplitude at any given time over the input amplitude. Now maybe the sinusoidal input system, maybe you can convert it into the output amplitude at steady state and then over the input amplitude. But at this one I am not sure, but I have to check. But usually the normal generic form is that output amplitude at any given time over the input amplitude.
Okay. And I know that we're like 4 minutes in, but one last really quick question. What's the difference between what is a step input? What does that look like? Is it just when it gives a piecewise function and that's it?
Okay, so sinusoidal input, you can see that it's like a sinusoidal
Yeah,
form,
like
and
exponential.
yeah, uh, uh, usually step input is kind of usually, okay, so it's difficult a little bit, but usually it can be described, a kind of the input change which becomes from 0 to at a finite value at a zero time 0. So that's how it's defined. It's like kind of how do I say, it's like, let's say, at time 0 you are considering some system, and at time 0 you consider that there is a change of value uh, at that 0 time, and the change of value becomes from 0 to any finite value. So this kind of input system is called kind of step input.
Okay, so it's kind of like a
So
piecewise function, like between 0 and 5, it's this. Between 5 to 10, it's another thing.
yeah, and usually okay, in step input, usually mostly computational system we use it more, like when you do the kind of what do you say, the computational programming or something, there we use this step input much more rigorously.
Okay, all right.
It's
Got it.
yeah, so it's basically useful to analyze any dynamic system. Usually it's gives the little bit computationally much more advantage.
Okay, awesome. All right, that's all I have then for today.
Okay,
Okay, awesome. Thank you for your help.
yeah, no worries.
Okay, bye.
Bye. Any dynamic system, usually it's gives the little bit computationally much more advantage.
Okay.